Right, so type 3 then is proofs involving inequalities. So type 1 was involving series, type 2 was involving divisibility, and type 3 for proof by induction is proofs involving inequalities. So we've got type 3. So before we get into the question, we need to get into a couple of rules of inequalities. So just a recap on the rules of inequalities. So recap on rules of inequalities. Okay. So if we take two numbers, or three numbers actually, we'll take three, element of R, so there could be any numbers because they're an element of R, then the following is going to be applied. So one, that if A is not equal to B, then either A is less than B or B is less than A. Okay, so if A is not equal to B, then either A is less than B or B is less than A. So for example, if we said that if 2 is not equal to 4, then 2 is less than 4 or 4 is bigger than 2. Okay, so if they're not equal, one of the numbers has to be smaller and the other number has to be bigger. So that was our first rule. Okay, 2 then, if A is less than B and B is less than C, then A is less than C. Okay, so if one number is less than another and that number is less than another number, then the first number is less than the last number. So if we put it together, if we said A is less than B, B is less than C, we could cross out the middleman and we'd be left with A less than C. Or if we said 2 is less than 6, or sorry, 2 is less than 5 is less than 10, then because of this, 2 is less than 10 as well. So we don't have to have the middle number in this rule. Okay. 3, if A is less than B, then A plus C is less than B plus C. So if the number A is less than B, and if we added a number to both of A and B, then the sum of the smaller number is smaller than the sum of the bigger number. So if we had, if say we said A was 1 and B was 3, and let's say C is equal to 10, that 1 is less than 3. If we add 10 to both numbers, 1 is still going to be less than 3. So if we add 10 to both numbers, so plus 10 and plus 10, we've 11 less than 13, so it's still going to be less than, your A is still going to be less than B, even if you add the same constant to both sides. So that's our rule 3. 4 then, if A is less than B and C is greater than 0, then AC is less than BC. So it's very similar to the third one. Instead of adding, we're just multiplying. So for rule 3, if you added to both sides, if you added a constant to both sides of the inequality here, then your smaller number will still be smaller. Whereas here, if you multiply a number to both sides, a constant to both sides, it's the same rule, just that instead of it being addition, we're doing multiplication. So we'll take the same numbers. A is 1, B is 3, C is 10. A times 1, 1 by 10, less than B times C, 3 times 10, 10 less than 30. So rule 3 and rule 4 are very similar. It's just that in rule 3 we're adding and in rule 4 we're multiplying. 5 then, if A is less than B and C is less than 0, so if C is less than 0, then AC is bigger than BC. So if A is less than B and C is less than 0, then AC is less than BC. And we'll do an example. So less than 0, not equal to 0, less than. So again, we'll take A is 1, B is 3, and C has to be less than 0, so we'll say minus 4. So A by C multiply, 1 by minus 4 greater than b by 3, 3 times minus 4 is greater than minus 12. So because we're multiplying both sides by a negative number, in this case the bigger number will have a bigger negative number, and when we look along the number line, or the bigger negative numbers are considered the smallest. So if we have our number line here, 0, 1, 3, so at the start b is bigger than a, but when we multiply it by a number that's on the left hand side of our 0, or the left hand side of the integers, a will go down to minus 4 and b will go down to minus 12. So this is AC and this is BC. So on the natural side b is bigger, but once multiplied by an integer, the negative of the integers, it gets reduced down to a smaller integer number, minus 12. So technically 12 is bigger than 4, but because it's a negative number, minus 12 is smaller than minus 4. And our last rule then, 6, is that a to be squared is greater than or equal to 0. And we know that from our algebra, anything squared, anything real squared is greater than or equal to 0. So they're just a recap on the rules of our inequalities. We might have known them already, but without knowing, without using our symbols or using a statement like this. So we might already have knowledge on these rules, but not in, I suppose, a more formal way like that. Okay, so we're going to get started on a question. So we'll go example 1 for proofs involving inequalities. Okay, so our questions magically appeared for us. Prove by induction that 4 to the power of n is greater than 4n plus 1 for numbers that are greater than or equal to 2, and for those numbers they have to be natural numbers. Okay, so for this question for inequalities, the P1 that we normally start with depends on what they're asking us in the question. So in this question it's 2, but in other questions it could be 1, it could be 4. So for inequalities we have to be careful with step 1 with P1. Okay, so we'll start with to prove first. So to prove that proposition n, 4 to the power of n is greater than 4n plus 1, where n is greater than or equal to 2 and n is an element of n. So that's our to prove, and we're going to have our proof now. So 1. So we want to show that proposition 2, so it's 2 because of this here, is true for n equals to 2. So that's our lowest number or base number for this question, and we'll sub in 2. So 4 to the power of 2 greater than 4 times 2 plus 1. 4 squared is 16, greater than 4 times 2 is 8 plus 1. 16 is greater than 9. Okay, so like before they were equal, but because we're dealing with inequalities, it doesn't matter if they're the same. What we want is that the left hand side is bigger than the right hand side in this question. So left hand side greater than right hand side, therefore proposition 2 is true. So that's our step 1 there. Okay, and we'll go to step 2, and we assume that PK, proposition K, is true for n equals to k, and we're going to sub k in then for the n part. So pk is 4 to the power of k greater than 4 times k plus 1. That's our first thing. We can't do anything more about that at the moment, and we'll go to the third step. Prove that proposition k plus 1 or pk plus 1 is true for n is equal to k plus 1, given that it is true for n is equal to k. And we're going to fill in k plus 1, proposition k plus 1. So 4 to the power of k plus 1 greater than 4 times k plus 1 plus the 1. So that plus 1 there is coming from this plus 1 here. So this plus 1 and this plus 1 is where that's coming from. And the k then is being replaced by this bracket here. Okay, and we'll just multiply out and make it look a bit better there on the right hand side. So proposition k plus 1 is, we'll actually split this as well while we're at it, we'll split our indices. So 4 to the power of k times 4 to the power of 1 greater than 4k plus 4 plus 1. Okay, and we know then from earlier that 4 to the power of k is the same as our step 2, 4 to the power of k, and we're going to sub in this entire side here. So p k plus 1 is 4k plus 1 times 4 greater than 4k plus, I'm going to say 5. And we'll tidy that up. 16k plus 4 greater than 4k plus 5. So then what we want really is, if we go back to our inequality, here we had 16 is greater than 9, so the left hand side is greater than the right hand side. So what we want is the same down here in our third step. We want this left hand side, we want this left hand side to be greater than the right hand side. Okay, so for the left hand side to be greater than the right hand side, we want, or we need, what do 16k plus 4 to be bigger than or equal to the right hand side. Okay, and what we'll do is we need to check. So we're asking ourselves, is 16k plus 4 greater than or equal to 4k plus 5? So is that true? And we're going to solve for k and see if that's true. So solve for k, and we've got 16k minus 4k greater than or equal to 5 minus 1. 12k greater than or equal to 4. K is greater than or equal to 4 over 12. K is greater than or equal to 1. Sorry, that should be 4 here, so this should be 1. So 1 over 12, perfect. So k greater than or equal to 1 over 12. So is 16k plus 4 greater than or equal to 4k plus 5? Yes, if this is true. Okay, so we're saying yes if k is greater than or equal to 1 over 12, it's true. So if k is not equal to or bigger than 1 over 12, then this isn't true. That's why we need our inequality with our equal to sign. And then we have our conclusion. So proposition is true for n is equal to k plus 1, given that it is true for n is equal to k, where n is greater than or equal to 2. And then we'll go and do, sorry, move that up. So we're saying yes, if k is greater than or equal to 1 over 12, it is true. If it's less than that, then it's not true, but we don't need to go into that for the proofs. We just care about when it is true. And then we have the proposition is true for n is equal to k plus 1, given that it is true for n is equal to k, where n is greater than or equal to 2. So we have our final conclusion then. So step 4 is our conclusion. And we're going back, so we've got proposition 2 is true, so it's 2 this time for that question. And then we have, if proposition k is true, then proposition k plus 1 is true. And then by induction, proposition n is true for n greater than or equal to n element of n. So there's our example for our proof by inequality.